Hello, this is Linear Algebra Math 2010, and in this lecture we are going to review the Gram-Schmidt procedure. So the first theorem that we mention here it reads as follows. Suppose that you have a set of vectors, they're non-trivial vectors, such that every vector in that set is orthogonal to every other vector. And so orthogonality, the point of this theorem is that orthogonality implies linear independence. So if the set is orthogonal, then the set is also linearly independent. And so this relates well with um, this procedure called Gram-Schmidt procedure, which is a recipe or an algorithm to build a set that is orthogonal. But the premise, unlike in the previous theorem, the premise is to start, or the hypothesis relies on starting from a set that is linearly independent. So here the set assumed to be linearly independent contains vectors v1, v2, v3, v4, v5, all the way through v sub p, and each of those vectors has a length m. And then the idea is that it will be possible to construct another set of vectors such that those newly constructed vectors are going to be orthogonal to each other. And so this construction will rely on basically a linear combination, a very special linear combination. So the secret is into computing the scalars and the vectors in that linear combination. So let's say that we call those vectors u. So given vectors v sub 1, v sub 2, all the way through v sub p, we are going to define new vectors denoted u sub k such that for a fixed index k, u sub k will be v sub k minus this quantity minus this other vector minus this other vector, etc., all the way through subtracting these other vectors. So what we can see here in this expression is that this is basically a linear combination. So we have vector v sub k, okay, and so that vector appears here is similar to the expression we had when we first talked about writing solution sets in vector form. We had then when we consider a solution set in vector form, there was a first vector in the sum. There was a first vector we called the fixed vector, and that fixed vector was added to a linear combination. So this is the structure of what we see here. We have a first vector v sub k, and then what we have after that is being subtracted. So we have a lot of subtractions here, minus, minus, minus. But we want to think of this, I can write minus, we want to think of this as alpha 1 u1 minus alpha 2 u2 minus alpha 3 u3, and then this goes all the way through, say, minus alpha sub k minus 1 times u sub k minus 1. So the important thing is that this new vector u sub k is something that looks basically like a linear combination, right? That all those terms are going to be considered a linear combination because they are no other thing than the addition of scalar multiplications, right? So each term on that addition, they're being subtracted, but you can just think of the minus alpha k as a scalar itself. Each term on that expression, each term in this expression, each of these alphas and u's is something that looks like a scalar alpha times a vector u. right? So you have a scalar times vector, scalar times vector, scalar times vector, all the way through here, scalar times vector. So you're adding up these plus that, plus that, plus that, plus this other thing. So this whole thing is really a linear combination, which is added to a fixed vector that is denoted here as v sub k. So when the new vectors u sub k are constructed in this manner, then we end up with a set T, which contains the newly constructed vectors u1, u2, u3, all the way through u sub p. And this new set T is orthogonal, but also it also has the property that the span of this newly constructed set, the span is equal to the span of the original set, right? So they have that property that the span of the set with the u's, which are the new vectors, this span is exactly equal to the span of the original set, which has vectors u v1 through v sub p, right? So the sets are not, the u vectors and the v vectors are not the same. The sets are not the same, but however, they do have in common the same span, right? The span of the set equals to the same set. So we're going to illustrate this procedure with this set here, with this example, and the first thing we have to check is linear independence, right? So what we're going to do is to check linear independence, we can easily create a matrix, store these columns. This is 1, 1 plus 1i, 1, that's the first column, then minus I, 1, 1 plus I, that's the second column, and then the last column would be 0, I, and I. And then what we need to do is to compute the RREF for this matrix, and we'll verify whether or not these vectors are linearly independent. So what we find by row reducing this matrix is that indeed this matrix row reduces to the identity, which implies precisely, it verifies that this set is linearly independent. So the formula says that we have an expression for u sub k, and this expression says that u sub k equals v sub k, always the first term in the sum. Remember, so the new vector is going to be a fixed vector, and then this fixed vector is going to be added to several vectors, each of which is going to be a scalar column vector multiplication. It's going to have this form, right? So, but the very first term of this sum is the vector that's v sub k of the same index. Okay, so and then it appears the first term that looks like this, and then the second term, and then the third, and so on, all the way. So this is an indication of where to stop. The last term on this expression is going to have index k minus 1. So when k equals 1, then k minus 1 is 0, and there is not such thing as a u sub 0, right? So that tells us that this term is not going to be there, neither the previous, and neither this term. So the only term that will be there will be v sub 1. Okay, so u sub 1 is exactly equal to v sub 1, which in this case is the first vector in the original set. Now, when k equals 2, so we take a look at this expression. This is the formula given by the procedure, right? And so when k equals 2, then k minus 1 is 1. So this tells us that we should stop. The last term on the expression would be u sub 1. Okay, so it says that all these terms don't appear there, and then when k equals 2, we're going to stop exactly at u sub 1, which means that we're only working with this part of the expression. So that means that u2 equals v2 minus minus that expression. Okay, so what we want to start thinking of is this part being as some kind of scalar alpha 1 such that this expression is looking like v sub 2 minus scalar alpha 1 times u1. So let's talk about this scalar alpha 1. So to compute that scalar, we have to compute inner products. And that scalar is defined as the ratio of two inner products, the first of which is the inner product of u1 and v2 in that order, right? So that means that we have to compute the conjugate of u1, and we have to use the entries of the conjugate of u1, and then multiply each of those conjugates by the entries of v2 accordingly. And so that's this is part of the calculation that's involved here. So this would be minus I plus 1 minus I plus 1 plus I, right? And then there's a couple of things here that this I can cancel with that I, for example, and then we end up with 2 minus I, right? So we are computing here that the inner product of U1 and V2 equals 2 minus 1I, for example. The other quantity that's involved in the definition of alpha is the inner product of U1 with itself. Okay, the inner product of u1 and u1. And so you may remember that this is exactly equal to the square of the norm of u1. And you know, either if you do it by remembering this is square the norm, or simply by applying the definition conjugate of u1 times you have to compute the conjugate of u1, which you had already done and used on the previous expression. Then multiplying the conjugate times itself, you end up with an expression that looks like 1 squared plus 1 squared plus 1 squared plus 1 squared, and this would be equal to 4. So that inner product of u1 times itself equals 4. So that implies that that scalar alpha 1 being defined as the ratio of these two inner products equals to this number, 2 minus I divided by 4, and then from here we can rewrite this as 2 over 4 minus 1 over 4 times I, right? And 2 over 4 is 1/2. But there you go. So this is an expression for that scalar, which is going to be a coefficient. Very importantly, that coefficient is going to be multiplying one of the vectors. So that means that the operation we're interested in is the calculation of alpha 1 times u1, right? So here is the vector, this is the vector u1, and this is alpha 1. So alpha 1 is 1/2 minus 1/4 times I, and this scalar is multiplying this vector, right? So when we carry out this operation, we will end up with a vector. So, and then, of course, I am writing steps. There are some steps that I am perhaps jumping ahead here. These calculations require very meticulous caution, right? So you're carrying out algebra computations, algebraic computations, and you have to be a very good bookkeeper. You have to keep track of signs, keep track of order of operations. All those things are very important. So you multiply this scalar times every entry, that gives you a new entry, and then I'm gonna just write what this looks like after you work and simplify a little bit. So the second entry would look like 3/4 plus I over 4, or 1/4 times I, and the last entry looks like 1/2 minus 1/4 times I, right? So this is what would be the vector that results from multiplying